Welcome to this deep dive into time series analysis. Today, we are exploring one of the cornerstones of econometric forecasting, the autoregressive model of order P, commonly known as the ARP model. Have you ever wondered how economists predict inflation, or how meteorologists forecast tomorrow's temperature based on the last week? The secret often lies in the memory of the data itself. At its core, autoregressive means a regression on itself. In a standard regression, we predict a variable y using some external variable x. But in an AR model, we use the past values of y to predict its future. The p in ARP represents the number of lags, how far back into the past we are digging to find patterns. Let's start with the simplest version, the AR1 model. Imagine you are tracking your daily mood. If today's mood is highly dependent on how you felt yesterday, you have an AR1 process. The formula looks like this. Yt equals a constant c plus a coefficient phi times the value of y at time t-1 plus some random error epsilon t. This error is what we call white noise, the unpredictable shocks of life. But why stop at yesterday? In an AR2 model, today's value depends on yesterday and the day before. In a general ARP model, we consider p past steps. Mathematically, yt equals c plus phi1 yt-1 plus phi2 yt-2 plus plus phi p yt-p plus epsilon t. This allows the model to capture complex cycles and momentum in data, such as seasonal business cycles or the lagging effects of interest rate changes. A crucial concept in AR models is stationarity. For an AR model to be useful for forecasting, its statistical properties, like mean and variance, must be constant over time. If the coefficient phi in an AR1 model is equal to or greater than 1, the system explodes or wanders off infinitely, creating what we call a random walk. This is common in stock prices, which is why predicting the market is so notoriously difficult. How do we decide the value of P? We use a tool called the partial autocorrelation function, or PACF. The PACF measures the correlation between yt and yt-k after removing the effects of all shorter lags. If the PACF cuts off after lag p, it's a strong signal that an ARP model is appropriate. We also use information criteria like AIC or BIC to penalize models that are too complex, preventing overfitting. In the real world, AR models are everywhere. Central banks, like the Federal Reserve, use them to model GDP growth. Logistics companies use them to predict warehouse demand. For example, if we look at the S&P 500 returns, we often find very little autocorrelation, supporting the efficient market hypothesis. However, in retail sales, the memory of previous months is much stronger. To summarize, the ARP model is a powerful lens through which we view the persistence of the past. By understanding the lags, the coefficients, and the white noise, we can separate meaningful trends from random chaos. As we dig deeper into the past, we become better at anticipating the future. References: 1. Gujarati D9, Basic Econometrics. 2. Box-Jepp and Jenkins GM, Time Series Analysis, Forecasting and Control. 3. Hamilton JD, Time Series Analysis. 4. Diebold FX, Elements of Forecasting.